The convolution model form allows us to take a discrete transfer function and express it in terms that are easier to use for computer calculations. It's an obvious form in the sense that if I were to take a transfer function like the one that I have here, where we have a numerator and a denominator polynomial in Z, you should be familiar with the idea that if this were the representation of a signal, that we could use our Taylor series expansion to write that signal as a straight sum g of z is equal to some constant plus c1 times z to the minus 1 plus c2 z to the minus 2 and so on. Now, in a previous video, you've seen us interpret this as representing the sample points at moments in time. So in other words, this would be C0, this would be C1 at the first time step, and this would be C2 at the second time step, and so on. So that would be 0, that would be delta t, that would be 2 delta t. And in the Laplace transform, we've come across this idea that there's this duality between the transfer function and the impulse response. And we can interpret this model form as being the impulse response of this transfer function. In other words, if I took this transfer function and I subjected it to a unit impulse, then this Z transform would represent the response of that system. But seen a different way, we can see that these coefficients form a single list of coefficients. Instead of having a rational function like this, we now have a single list of coefficients which we can actually numerically convolve with an input signal in order to obtain the output of that system that would result from inputting that signal into the system. And I want you to see the parallel between these two model types. So in other words, when we had u of t and some impulse response of time in the box, and we had y of t outside, we would write y of t is equal to the convolution integral g of t times u of t. And it's this, if I Laplace that, the Laplace transform of that signal in time translates to multiplication in the Laplace domain. And so by analogy, we can say that if we had some u of z with a g of z, now this seems quite obvious, but we've had to prove that this is the case, that we also have y of z is equal to g of z times u of z. And what that corresponds with in terms of the analogy with the time domain, so in other words, when we took a transfer function in the Laplace domain and we multiplied by an input signal in the Laplace domain to get an output in the Laplace domain, that corresponded to continuous convolution. And when we do the same thing with a discrete system, we end up with something that corresponds to discrete convolution. And so we would write y of z is equal to g of z times u of z, but that would actually translate to a convolution form. And remember now, the time version of y is y of k, where we have this C0 plus C1 times U of K minus 1 plus C2 times U of K minus 2, and so on. And basically what we're doing is we're convolving the input signal U of Z with this coefficient matrix that we or this coefficient vector that we obtained over here.